Welcome back to another video on building an EDR from scratch. So in this video we're going to actually build a block using what we've already put together. So this file here is a remote process injection. So it opens a process, uses virtual alloc to allocate some memory. It writes to that memory the shellcode that it showed above, and then it executes the shellcode using create remote thread. So we're gonna go through, we're gonna add a couple of new hooks, and we're gonna build some blocks to block this payload. So first thing we want to do is just compile this, make sure it runs, and just kind of get an idea of what it looks like when it executes without being blocked. So I'll just copy this file path, paste it into PowerShell, and run it. And you can see here it's looking for notepad.exe, but it's not found. So let's open Notepad and rerun. It's searching for the process. There's a 5-second delay that's written in, or 5-second sleep, so that's why this takes a minute. So we'll just press enter through all of these, and you can see that Notepad closes and our calc payload executes. Okay, so let's open up another tab, and let's also run the agent. That way we can get an idea of what the hooking DLL is seeing right now. So before that, we need to, since we're just using the agent in this video, we're going to add some logic to, okay, so there's an error on the file system file, and that's just because we need to update our C language standard to C++ 20+. That way it knows what that file is, essentially. Okay, so we just want to add some logic here. So we're going to add in argc, argv, and what we want to do is be able to pass an argument. This will be a boolean of kernel, and we'll start it off as false. And if we have an argument, so if our arg count is equal to 2, and the argument in argv1 is equal to kernel, then we'll set our boolean kernel value to true. Otherwise, we'll just set it to false. Or you can just do nothing here, however you want to do it. Okay, so then using that variable, we will we'll just say if bkernel is true, then we'll do all of this kernel stuff. Otherwise, we just want to ignore it, and that's essentially for the purposes of this video and like building out our hooking DLL even further. That way we can just ignore the kernel piece. All right, so now let's try to build this, make sure everything works as expected. So open up our PowerShell window and paste in our vagent executable path and run it. You can see that it's running just fine. It's not doing any kernel stuff since we didn't pass the kernel DLL, or the kernel argument. Okay, so now rerunning the process injection payload, we can see essentially what we've written before. So we see the page execute read write permission detected, our hooks are installed, and that's really about it. But we want more, so let's do more. So let's jump over to the hooking DLL, and let's add a couple more hooks into a few more API calls. So what we want to hook create remote process. We want to hook write virtual memory, and we're also going to hook open process. Okay, so let's start building out our type definitions. I pasted in the type definitions here. Let's now let's add our pointers. So we'll do pointer to int create remote thread, and the variable name will be pointer to original create remote thread. That'll be null, just like the others. And we'll do that for the other two. So pointer to original int write virtual memory. Sorry, not original. Just pointer to int write virtual memory. And then the variable name is pointer to original int write virtual memory, and that'll be a null pointer as well. And then a pointer to open process. That will be the variable name pointer to original open process, and that will be null as well. Okay, so we have our type definitions, we have our pointer variables. Now let's build the hook functions. Before we build the hook functions, let's add a another if statement here. We'll say if hooked, and then we're going to put all of our logic inside of that. That way we're not none of our logic happens until after we set this variable to true. So we'll create bool hooked. This will be global, and we'll set it to false first. And we'll pull all of our logic inside of this if statement, and this will help get rid of some of those false positives that we have right now. Then we'll take this, copy it, and bring it down to our hooked int protect virtual memory function as well. Pull this inside of it. And then we just want to go right under where we initialize our hooks, and we'll set that variable to true, and that will essentially turn on our logic that we're writing. Because we know from experience that some of the calls to API calls to install our hooks are kind of flagging the logic that we've already written, and we want to remove all of that. Okay, so first thing we want to do is create our hooked function for write virtual memory. So we'll come down here with these arguments. We'll create a dword int API hooked int write virtual memory. We'll paste in the arguments, open and close the function, and then we'll just write our return. The return will be the pointer to the original int write virtual memory. And we'll just copy paste these arguments again. Just clean this up, get rid of the type names, and just bring everything to one line. And it looks like we have an error. all of the argument names look correct or in alignment. Oh, okay, I see. Looks like I copied the arguments from the wrong function. So that was my mistake. Wasn't paying attention to what I was doing. I was on autopilot. Okay, so from NT write virtual memory, we'll copy those function arguments and paste that in. And then we'll just copy paste these across. Okay, so that looks better. No errors or anything. Okay, so now let's do the other two. I'm just going to copy these type definitions and bring them down, paste them down here underneath the hooked function that we just created, just for easier reference. So next we'll do create remote thread. So this will be dword nt API hooked create remote thread, and we will copy paste our arguments again. And then write our return. This will be return to the pointer of the original create remote thread, and we can again bring over our arguments. I think every time I paste these arguments, I do it a different way, just searching for the fastest way to do it. It's all kind of slow and repetitive, but we will get there. And one more. Okay. Add our semicolon. That should be it. Return value doesn't match. Oh, okay. That's because we have our return value as a dword, and it should be a handle. Then we'll do the open process function. This should actually be win API. And the create remote thread should be win API as well. Sorry about that. So this will be a handle, win API, and this will be hooked open process. And we'll just copy paste our arguments one more time. Maybe, if we can do it right. There we go. Then we'll open and close the function, and one last return. So this will be return pointer to original open process. Paste in our arguments. Clean this up. There we go. Okay, so, and that'll be it for the function hooks that we're adding in this video. So that's 3 additional hooked functions. Now let's add our if hooked logic to each one of them. We'll just copy paste it into all of them. Okay. So with that, we need to initialize these hooks now. So we'll go into our initialize hooks function and just copy one of these if statements. And we'll need one of these for each new hooked function. So our first one we'll do int write virtual memory, and can just copy this and kind of just paste it around. Paste it there, and then we will paste it here. Looks like I'm not great at pasting, but okay. The next function we'll do will be from kernel 32 instead of ntdll, and this one will be create a remote thread. And we can just copy paste that again. Copy paste it around. And get rid of this extra nt up here that I missed it before. And one more function. So this one will be in kernel 32 as well, and it's just open process. And just paste this around. Okay, now let's try to build the hook DLL. It built successfully. Okay. So, since it built successfully, we're just going to continue forward. And the first thing we want to do is build a structure. This structure is going to track each process that we interact with, or that our parent process interacts with. And the primary purpose is to try and determine if a process is attempting process injection. So we'll call this process tracking info, the structure. It's going to have a Boolean allocated executable memory. We'll start off by setting it to false. And this will just be used to, or whenever our parent process allocates executable memory, then this variable, or this Boolean variable, will be set to true. Then we'll do another Boolean. This will be wrote to executable memory. This means that the parent process wrote some information, doesn't matter what it is, wrote something to the allocated memory space. And then we can store the base address. We can use this later on just for like scanning purposes, or if we want to inspect the data that's been written there, we can inspect it using this base address. And then the size, we get the allocated region size. We'll set this to 0 for now, and this can also be used to isolate this memory space for scanning purposes or inspection, whatever we want to do later on. Or if we just want to like zero it out or something as a defense mechanism, we can do that as well. Okay, now we'll create a map to track all of these processes. All of the processes will be tracked in each individual process. So this isn't something that's going to be stored like in the agent. It's just going to be tracked in each individual process or instance. So we need to include unordered map. Then we're going to create an unordered map. It's going to take a D word as the key. And it's going to have the structure process tracking info. And the variable name will be process tracking map. Just add to the comment that the key is going to be the PID. So whatever PID is being targeted will be the key. Okay, I'm going to remove this comment now that we're done there. And we can get started writing some logic. So the first thing that we want to do is get a PID. That way we can track the process essentially. So we'll add this to a variable. We'll use get process ID, and whenever memory is being allocated, we'll immediately call get process ID. And if the PID is not equal to 0, then we're going to start doing something with it. So we'll bring a previous print message where we're printing out that it was allocated with read write execute into that secondary if function. We'll just modify it to make it look a little better, just to hold us over. This definitely needs to be rewritten into some format like JSON or something. That way it can be digestible by something else later on. But for now, this is good enough for the basics. So we'll do int allocate virtual memory, page read write execute permission detected on PID. This will be whatever PID we get out of that process handle. So we'll print that out. That'll be logged to our agent. Real quick interruption. Make sure that you subscribe to Evasion Games if you're interested in practicing or learning EDR evasion, just like the content in this video. It's going to be an awesome time. And then just below this, we can say if PID is not equal to get current process ID. So we'll check that the PID is not our own process. And if it's not, then we're going to deem this as suspicious. It's definitely not, like this could definitely like trigger false positives, but for our purposes, we don't really care. This is more for learning purposes. It's not going to be like deployed to production. So it is definitely possible that a legitimate application could allocate memory with page read write execute on a remote process, but we'll say less likely. So we'll just write suspicious memory allocation attempt detected on PID. Can just remove this for now. Say PID, and then PID equals okay, and then we'll just say with page execute read write permission. Being indecisive, but we'll just do with page execute read write permission. And then we can return null. So instead of returning a memory address, we just return null. And this is our hook really like actually for the first time taking some action instead of just passively logging. So we can test this now, but we're going to comment this out and write some more protections, but for now we can just test this real quick. So we'll build vhook and rerun the process injection. And we need to open Notepad. Okay, so now we should see the suspicious allocation. Here we can see suspicious memory allocation attempt. And since we're returning null, the process injection is essentially broken. Like it won't work. But everything else continues as if it were going to work because we weren't. There was no like error code or error handling like properly written into that process injection. So it still attempts to execute, but there's nothing for it to execute. Okay, so we'll comment that out for now. We'll just log it like we were before. And then we want to update our map. So we'll create a variable tracking info, and it will point to our process tracking map keyed with the PID from the process handle. And we want to update the Boolean allocated executable memory, which just happened, right? And we want to set that to true. Then we'll take all of this, bring it down to NT protect virtual memory. Since this can essentially do the same thing, it's not actually allocating it, but it can set the permissions to page execute read write. So we'll keep the same logic and just update it to fit. That way, if the protections are ever changed to page execute read write, we'll still trigger that Boolean on the PID. There are definitely ways to get around this, like 100%, but this should give the basics for sure. Okay, so we'll bring this and just paste it again into write virtual memory. Here we're going to add a little more logic. So first thing we need to do, since I deleted it, is get the PID. That will be on the process handle. And then we want to loop through our unordered map and see if we can find an existing PID. So we'll say if process tracking map dot find the PID. It's not equal to the process tracking map end, so that means we didn't get to the end of the list. Then we want to so if we didn't get to the end of the list, we want to create a log. And this will be int write virtual memory called on previously allocated PID. That just means that we already have an entry for this PID where it was allocated with executable memory. And then we want to update our tracking map. So we'll bring these variables up. And we want to change this to, instead of allocated executable memory, we want this to be so we'll do another if statement, and this will be if allocated executable memory does exist. So we want to make sure that it exists. And then if it does, then we will log a message. This will be int write virtual memory called on previously allocated executable memory. We'll bring the PID down. We'll say executable memory for PID. And then we'll end it with potential code injection detected. So this will be our first alert that something suspicious is happening. And then we need to update tracking info for this PID. And we'll set wrote to executable memory equal to true. And then we'll add some logic to hook to create a remote thread. We need to change this to H process because that's the handle variable name. And then we'll do the same process tracking search, but we want to instead update our secondary if statement to look for allocated executable and wrote to executable. So if both of those happened, and now we're calling create remote thread, then there's a pretty high chance that there's code injection or process injection, code execution happening. So we'll change this create remote thread called after memory allocation and writing. For PID, that'll print our PID. We'll say code execution detected. And then we'll just return null. And then if we build this, we'll open Notepad and we can rerun the process injection. You can see hooks installed successfully. That's what we expect to see. NT-write virtual memory called. Potential code injection. You can see that where we wrote to executable memory. Looks like it's printing a lot. It's probably some copy paste error in there. So you can see potential code injection detected. You see it multiple times actually. So if we continue, now we can see we just wrote the shellcode into the process. And most of all, everything that you're seeing right now is a lot of false positive because of some pasting error that I probably made. But now you can see when we try to create a remote thread, we get the message code execution detected, and we don't ever get our shellcode execution. Our notepad is still running. Shellcode execution never happens. No calc is spawned. So the block worked as intended. We could definitely clean up the logging a little bit though. Okay, so now let's write the logic for our hooked open process API call. So for this function, all we're really going to do is just check if it's hooked, and then we will just log some suspicious activity or suspicious permissions opening. So let's find our hooked function. Here it is, hooked open process. Okay, so we'll just say if hooked, then we just want to log a message not just as if hooked. So if hooked with desired access, bitwise, process all access. So if we open the process with process all access, then we want to log suspicious open process call. This could definitely trigger a lot of false positives as well, but it gives us some initial information. So we'll log suspicious open process attempt with process all access to process ID. And then we'll just put in our process ID. So we'll do std to string dword process ID. That's an argument that's already passed into this function. Now we'll rebuild vhook, and we can run it again. Let's uncomment this protection. That way we get the full effect. Okay, so we run this, we can see our call, suspicious open process call with process all access, with a typo, bunch of typos, potential code injection, and that is essentially it. So we have 2 protections applied with some suspicious activity being logged. I hope that you enjoyed this video. The next one's going to be pretty good as well. The next one will definitely do some more kernel work, so I hope you're looking forward to that. I also want to note that I did create a release in GitHub for this code. So all you need to do now, if you have issues compiling, just download it and you can run it straight from there. Don't forget to like, comment, and subscribe. I really appreciate your support. Look forward to the next video next week. Thank you for your time.